Next up, we do have Justin Garrigus. Did I say that correctly?
Garrigus.
Garrigus. I added sounds on accident. My bad.
That's okay.
Justin
I
Garrigus.
love sounds. I love adding sounds to things.
Yeah, Justin, software developer. A talk about creating robust modular AI through abstract models.
All right. So this talk is going to be about making AI in a game, and it's specifically about making modular and robust AI through the use of automata theory. So before we get into any dense math stuff, it's not going to be too dense. It's going to be fun. This isn't necessarily geared towards programmers or anything, but I think anyone can benefit from learning about automata theory, specifically because it just uh, introduces a new way of visualizing things, especially in terms of games. Like you'll notice a lot of games are really state based, and that's what this is all about. So this is a video showing off a game I made just to show off my qualifications, sort of. My name is Justin Garrigus. I'm a computer scientist at UNT. I'm a programmer for this group called Enemy Spawn, and I have made a few games, including Decomposition, which was one of the games that was submitted for the Society of Play Trick or Treat Jam. And let's sort of begin. So, what is an automaton? By the way, this is very cool because the previous presentation was about, Matt's presentation was about regular languages, which this wasn't planned, but I'm very glad that we had this sort of coordination. Anyways, an automaton, you may have seen in the presentation before, is the formal definition, an abstract self-propelled computing device which follows a predetermined sequence of operations automatically. Very dense way of saying it's a thing that verifies if input is correct. The main idea is that I, a programmer, input to it a string, like let's just say an email address, and it outputs to me whether or not that string was actually correct or incorrect. Very abstract terms which may depend on the situation. But in this case, it tells me if that email address I inputted was actually an email address. There are several different things we can do to check this, like just semantically, we can just see, all right, the string has an @ symbol in it. After the @ symbol, it has a period. And after a period, there are 3 or more characters, right? So that would check pretty much anything like a standard email address, right? On the flip side, I can put in strings that aren't necessarily English, or maybe it's just random garbled text, or maybe it's very similar to an email address, but it's just a character off in some way, in which case it can provide to me an associated error message, maybe, that tells me why it was incorrect or something. But we're going to get into today about how we can create automata and how it actually relates to artificial intelligence in games. So, here is an example of an automata. We have the objective of this automata we are going to create, which is it should accept all strings that begin with the letter A. We are given strings as input that contains either 2 letters, a group of 2 letters, either A or B, right? On the right side, we see 6 different possible inputs. It can contain infinitely many inputs, but these are 6 that we can test it against. We can see here that the different inputs that would work are 1, 3, and 6, because each of these strings begin with the letter A. The rest of them, they have the letter A in it. The rest of the strings have the letter A in it, but they don't begin with the letter A, so they are not accepted, right? This is a very simple example to sort of simulate much more difficult things. This seems trivial, but we are going to get into much more complicated things that can only be simulated with automata. So let's go ahead and create it. We have our starting state here. An automata is defined by a starting state, some arrows that lead to different states, and a final state, or maybe even trap states, and we'll see what that all looks like. But we have this starting state. We enter into Q0. Then, if we were to see the letter A, if we consume a string, and the string, the very first character is the letter A, then we know that it should go to a new state. So in this case, it should go to Q1. Now, we also need to handle if the first character is the letter B. So that's going to be to this state right there, P2. It should have been a Q, ignore that. Anyways, we have that state, and if we see the letter B, then we will go over to P2. If we see the letter A, we will go to Q1. All right. Now, we have to handle, what if we consume the first letter? Where do we do next? What do we go next? What do we do? If we see the letter, if we are in Q1, and we see either the letter A or B, we don't need to do anything else. We're on the correct state. We have consumed the right input. It's correct by our standards, anyways. So we can just say, just go to the same state over and over again until the string is finished being read. Similarly for B, if we start with letter B, if the very first letter is B, then we already know it's failed. It's failed as an input. We don't need to do anything else to it. So let's just keep reading all of the input until we are done. And there we go. All right. So let's see an example of how strings are read using Automata. So here's how it looks like. We have our current string we're trying to test, which in this case is A, B, A. All right. We have our starting state, which is right before the input is read. And we have our three letters A, B, and A. And we have our ending state, which is after the letter is read. And let's just see how it looks. We start with the start arrow. We can tell it's a starting arrow because it does not have a state before it. But we consume the first letter. We read the first letter, and it is A. So from Q0, we follow the arrow that has a letter A on it, in which case it is this arrow leading upwards, and it goes over to Q1. Then, even though, so we can tell what an accepting state is because it has a double line on it. So Q1 is accepting, P2 and Q0, they are not accepting. All right. We don't want to end right here. We want to consume the entire string. So even though this is a correct string, we have already verified, I mean, just looking at this, it's not going to go anywhere else. But with the point of the automata is we're supposed to consume the entire string. And once we finish consuming the entire string, then we can know that it's correct or not. So in this case, we are consuming every letter. We consume the B because the arrow just points back to itself. Then we consume the A, so it just points back to itself. And finally, we end. There's no more letter left to read, so we know this is an accepted state. All right, so here's a little bit more difficult example. This is an automata, which is the purpose is to verify if strings are correct, and strings are only correct if they have an even number of zeros in them. Just sort of looking at this, we can see there are two states. The first state is accepting, which we can sort of glean that E, the E state right here, the E input, I mean, is correct because it doesn't have any input to it, but also, I mean, it has an even number of zeros in it. There are 0 zeros, I guess. So this is correct, right? If we just enter this state and we just don't do anything else, and then that's good string. Similarly, if we were to see a single zero, or in this case, an odd number of zeros, we go over to S2. And this does not have a double circle around it. And any ones, it will just repeat itself over and over again. It will just stay at S2. And this is true for all these inputs. In this case, B, C, E, and F, they are all accepted. A and D are not accepted because they have either no zeros or an odd number of zeros. Actually, I just realized A is accepted. That I think I said it wasn't accepted. A is accepted because it has an even number. 0 is an even number. I think only D is not accepted then, because we have 1 here. It goes loop back around and it loops back around again to 1, and the next one is 0, so it goes to S2. Then it sees a 1 again, and there's no more input to read, so it just ends right there. Here's a much more difficult example. The purpose of this automata is to verify floating point numbers, so decimal numbers inside of a programming language. This is like the actual reason. The previous examples were trivial. You can just use that with any other programming language really simply, just with for loops and stuff, even just like .contain statements. But this is our first example where we actually need an automata. So the idea is the letter D means a digit, so 0 through 9. And the purpose of this is to verify. So all these examples right here at the bottom, those are all correct. So those are all floating point values. And we can see here, if we see a sign value, if we see a decimal, we can see as many decimals as we want. We can see a decimal point, I mean digit, not decimal. I guess it's the same thing. If we see a decimal point, another digit, as many digits as we want. So this area represents like the point after the decimal point. Then we have our exponent, the letter E itself. Then we have a sign for that exponent. And then as many digits as we want to represent the number of the exponent. So you can go through if you want in the video posted later, just verifying each of these because these all work out. And maybe you can try things like maybe if we had 2 decimal points, you can see this would either not be read because we don't have any state that accepts 2 decimal points, or if you have a weird layout, it may just end on an empty state, which does not have 2 rings around it. All right, I got to speed up a little bit. So, some usages of automata theory is regular expressions are a very big one. Regular expressions are just automata theory, just automata. With text parsing, things like JSON and YAML and XML just have to verify those things are correct. Protocol analysis, things like wires, they have to check to see if signals sent to it are correct signals. And natural language processing, things like that. This automata right there is meant to verify for things like a programming language. So if you have a language, you need to know if the text is an ID or an if statement, or maybe it has letters after it. So it is an ID, maybe it is a number or a decimal number, things like that. So how does it relate to AI? And we're going to talk about, so previously we were talking about automata, which is a very broad definition. A finite state machine is an even broader definition. And the purpose of a finite state machine is that it does not have an accepting state, and it does not really have characters it needs to verify. It's more about being state driven, like conditional driven, basically. And transitions are defined on a per state basis. We will see what that means. And we will show an example of a really cool finite state machine in the example of Pokemon. So in Pokemon Sword and Shield, this has a very good finite state machine that I really like, and it's very simple too. It is specifically in the sort of overworld section, not the battling section, is when you have Pokemon that sort of walk around and they may want to battle with the player by running towards them. So we're going to define a few different states that these Pokemon share. There is the idle state, which means they just sort of stand still. They have the walk state, which means they just walk, they pick a direction to walk in a few seconds and they just do something else. We have the curious state, which means they have a question mark above their head, they see the player, and they sort of walk slowly towards the player. The player can easily outrun them, though. There is the alert state, which is a lot more aggressive, I would say. The Pokemon has an exclamation mark, and they sort of run towards the player. Finally, we have the return state. So if the player manages to outrun the Pokemon, then the Pokemon needs to return back to their original area. Right? We don't want the Pokemon to just like continue following the player forever and ever. So, some observations about these states is that they're very self-contained. Each of them contain a unique action as well, and states lead to new states based on clearly defined actions. We'll see in just a second how easily we can define these actions. So here is our start of our automata. We have our two states, walk and idle, and these states represent actions. That's the important part. These arrows here represent conditions that lead us to changing actions. So that's going to be an important distinction we will see in the future also. So whenever this condition is true, then we switch states. So if we just put this into our game right now, we would just have Pokemon that just pick a direction, walk in for a few seconds, and just keep changing directions, basically. So now let's add in our new state. Let's say a notice state. This is a new one we have not discussed previously, but it's just for organizational purposes. But if at any point the AI sees the player when they're in these two states, then they're going to go to the notice state. Now, the notice state is just a single frame long. It doesn't have any action inside of it, but it does lead to two other states depending on, let's just say, an aggression value of the Pokemon. That is fluid. We can define what that means in the game itself. But this leads to either curious or alert depending on how much aggression the Pokemon has. And now we have our return state. So if at any point the player is too far away, then we go to return. And if we return back to our original location, then we just resume idling. Now, why do we use automata? Well, this is actually, as you can see, this is very easy to visualize. The alternative is just to use loose code, I guess, that controls what happens. This is much more organized than alternatives, but we can actually implement this very easily also. My personal favorite example is to use enumerators and delegate methods. We can also use switch and enums if we really wanted to, but this finite automata is actually very easy to bug fix as well. Like if we see an AI that's sort of like looking all over the place and maybe it runs very fast, right? We know exactly what caused this because we such easily defined the different states that the AI could be in. And it's also very scalable and modular, which we'll see just now, how scalable and modular it is. We have two different groups here, passive and active, which we can add on top of our existing automata. These don't really offer new functionality, they just sort of organize things. And also, let's say we wanted to add a new state to it. Let's say a greet state, right? So this is just like two Pokemon, they see each other, they do an animation, and then they just proceed or something. So we can add that easily into here. Let's just say after idle, it goes to the greet state, does its animation, and it concludes. But still, because it's in the passive area, if in the middle of its animation, if it sees the player, then it goes to noticed. So still very simple in that regard. And that is everything I wanted to talk about today. So the main idea, summarize things, automata, they're very easy to organize code. They're state driven. Save yourself the trouble. If you're making a complicated AI, you can add complexity very easy to an automata. It's very easy to do. You just need to make a good framework, and automata does a very good way of doing that. Abstract models in general, they're a very good way of organizing things. And that is everything I wanted to talk about. So thank you for letting me talk about circles and arrows.
Awesome. That is very, very cool. Thank you so much.
Of course.
Big fan. AI hard, programming hard, and that makes it a lot easier to understand what I'm trying to do when I make AI.
Yes, I my previous game I remade the AI like 4 times, and then the fourth time I used just this model. That's why it's very good to use.
Awesome. Thank you so much.